Okay, so this section is over principal components analysis and exploratory factor analysis. And mostly we're just going to do an example of EFA, but you have to talk about both so that you understand what the differences are. Make it a little bigger here. So this is going to be a complete departure from everything we've done all year. Oh, good. In a good way. So I would describe these as descriptive analyses. The point of them is usually to take a large data set and understand the relationship between the variables or the sort of patterns of data. Now, if you've ever taken a any type of standardized test, the GRE, ACT, SAT, the WISC, the WASTE, all those IQ tests, what they've done is they've taken many, many questions and tried to figure out the pattern to understand these, like, what are called latent variables underneath, so unmeasured variables. And so EFA is like the first step usually in those procedures where we're going to group all of our different variables together based on having high correlations between them. So you actually want multicollinearity in a sense. And it's based on their patterns of answers. So if you think about a scale that you've taken, or you can look at the scale that we're using in this example. So the one on this example is a self-determination theory scale about college. And so a lot of these questions have a similar theme, because they're all on the same scale. Otherwise, why would they be on the same scale? So why do you go to school? That's sort of the question. I need to get a degree to show myself that I can succeed. The starred ones are negative. I wonder what I'm doing. I actually find it boring. So what we're trying to do is take those patterns of answers and find the underlying factors in those. So this is often called data reduction technique. Okay? And SPSS is actually listed under data reduction. So PCA is principal components. And I'm going to need a marker for this one. So what PCA does is it takes the questions and creates components. So we need a marker that right. So about PCA over here. Over here. So let's say we're trying to measure, in self-determination theory, it's often about intrinsic motivation, autonomy. So let's say we're trying to measure motivation. And so anytime you see a circle, that means it's unmeasured. So circles in any type of structural model are unmeasured. But we can't just make up numbers, so we're going to include some measured variables. So this is where your items or your questions would come from. So I've got, let's say, 3 items that I'm trying to understand if they measure motivation. So there's not quite enough room over here. So for principal components analysis, or PCA, it's this idea of components. And the thing is that the questions, or the items on your scale, cause the component. So the questions predict the component, so the arrows go this way. So anytime you have an arrow, it's like X is predicting Y. That's more traditional regression, where I have all of these variables that create a predicted score. So the variables cause the component, the latent score. So we could combine those together and create this overall motivation score, and that's traditionally how you treat scales. I add them all up or average them. The problem with that is that that's not generally the way, at least in psychology, we think about underlying variables. Instead, we're going to do factor analysis. And the idea is that the factor causes the answers on the questions. So this is a theoretical. So the arrows go the other way. So X causes these little Y's. And the easiest way to describe that is to talk about IQ. So I'll talk about IQ a lot. I don't think that the questions on the Stanford Binet or the WISC cause your IQ. Like, That's not a thing. It's not like by taking the test, I got an IQ. So that would be great, but it's not how it works. Instead, we think that the questions measure your IQ. So IQ is causing the answers on those questions, and those questions are just the way we're assessing it. I do not know what is going on at all. So, traditionally, most psychologists use EFA because we think that this underlying latent variable causes the pattern of answers we're seeing, not that because we gave them this question, we get these answers. Okay. So think about that in IQ terms. Like, I think the IQ causes the answers on the questions, not the other way around. If you're going to do PCA, you talk about them being components. If you run an EFA, you talk about them being factors, and what's different is the underlying math. For PCA, we're going to use all the variance, so it'll analyze the total variance. For EFA, you get shared variance. So we're looking at just the variance, like r squared. So you're analyzing just r squared, and the rest of it's error. So the big theoretical difference is the direction of the cause. So if I ask you what's the difference between the two, it's the causal direction. So PCA, the questions cause the component. EFA, the factor causes the question answers. And that's the first bullet point on each one of these. That is not my mouse. So kind of explaining what I mean by the different variants. So common variance, which is sometimes called commonality. And then on the output, commonality is listed as H, because C would be too easy. Commonality is the shared variance between items. So if I have these 4 questions, commonality is the fact that these overlap. Okay. Unique variance is variance that doesn't overlap with anything else. So this is totally unique, and this is partially unique. So unique variance is usually considered error, because it doesn't overlap with anything else. So EFA describes only the common variance, so variable 4 would be bad. PCA tries to describe both. This says commonality equals 1 because this question is completely subsumed by all other questions. This one is 0 because it's all unique variance. So on the output, you'll see commonality and unique variance, and then a measure of complexity, so kind of how useful the question is. So some other things we're going to get, so lots of kind of new terms. The biggest, scariest term is going to be eigenvalues. Let me start with correlations. So the observed correlation matrix is what we've been calculating all year by using the core function. And so it's just a correlation of all the different variables. Okay. You're trying to explain that correlation matrix with your analysis. So here's what I have. How can I group them together and end up with the same pattern of correlations? So that's the reproduced correlation matrix. So if I create these factors, can I reproduce this table? And mainly, we're interested in the last one, the residual matrix. Okay. The residual matrix is the original one and the reproduced one. Not reduced, reproduced. And they subtract. Okay, so the residual matrix is the error. So I have this set of correlations. Here's my model of those correlations, subtract. And we're going to use the residual matrix to tell if our model is any good. So really for me, like the point of doing this, and we're getting to research questions here in a second, is to create a picture of all the questions that you have. The way we do that is called Eigenvalues. You had a real math class, you've probably talked about these. But what eigenvalues are is it takes the correlation matrix. So let's say we have 5 questions. Right, we've got them all correlated. 5, so all this is 1. Right. And let's see. Wait, 2. I've lost my rows here. What you're doing with eigenvalues is trying to take a correlation matrix and reduce it into smaller number of things. So the point of factor analysis, or PCA, is to take all this data and make it smaller. And what you'll do is you'll say, well, these questions are all really correlated, and these are all really correlated. They're a way for me to take those high correlations grouped together and make that, here's factor 1, here's factor 2. So eigenvalues are a number that represents the groupings of questions. They are not standardized, so they can be 6, 8, 12, 20. It is a representation of the variance. Fortunately, you'll also see how much variance they account for. That makes a little more sense because that's proportion. The confusing part is, if I want to say, let's do 3 factors. I think there are 3 factors with this model, let's try 3. And you have 30 questions, you'll still get 30 eigenvalues. So you'll get as many eigenvalues as you have items on your scale. Because this is sort of calculated before the analysis. What you want to look at instead is how many of those eigenvalues are big. So what happens is, why do I get as many as I have questions? It groups them together and it goes, well, crap, what do I do with this thing? And then what do I do with these 2? And so it will still try to combine the leftover ones. They just won't be very good. So the way I think about eigenvalues is it's a representation of the groupings, and only a couple of the groupings are going to be any good. Mathematically, they're very complicated. Not worth going over. So why would I do this analysis? Often the question is, I have this new scale, and I want to know if it does what I think it does. So this scale is supposed to assess 3 different things. Does it? Do my questions line up where I think they line up? So I do this a lot for other people because I like EFA a lot. And so, for example, a paper that finally got published, forever this example was like, one day this will get published, but finally. Fram was interested in assessing fight or flight and also a freeze component. So some people just like freeze up and they don't punch or run away. Okay. We went through that sucker 5 times before we finally got 3 factors. So we had all these different questions, and she had a theoretical component. This should be fight, this should be freeze, this should be flight. And I'm like, yeah, no. She's like, but I need them to go here. I'm like, no, it didn't. So it took us, she was expecting 3, and it took us a while before we finally got the scale to do what she wanted to have be 3. You can also test other people's scales. So they say the scale has 5 components. Does it really? We did that with a anxiety and depression scale. So it's supposed to have 6 factors. So did that work? And it did. Okay. If you're actually developing your own scale, though, it can often be just kind of a question. Like, I think most of these questions are probably pretty good, but I know some of them are bad. So it'll let you eliminate questions that aren't important or that are not very good for you. So my other story about that this paper hopefully one day will get published. Graduate student working on a question about how people feel about clinical therapy. And she had this question on here, and every time I think about it, I laugh. She said, how pretentious do you think this therapy is? But none of the freshmen knew what that word meant. So in later versions, she had like snobby and uppity, like next to the word pretentious, and that question never stuck. Like, every time it would come up and be a bad question, I would just laugh because I just didn't know what it meant. Sometimes people don't interpret questions the way you think they do. So this analysis will let you do that. So a lot of EFA is just like, let's just throw everything at the wall and see what happens. Because that's essentially what you're doing. All right, power. This is the first time you hear me say the more variables, the better, and the more people, the better by a landslide. So there are ways to calculate exact power, but it's kind of not worth your time. There are general rules. Either the model's going to work or it's not. So you need lots of participants for this type of data. That's why people don't do them on like smaller subsamples. So if you wanted to study a clinical population, it's hard because you can't get enough people. Usually you'll test your scale a couple times. Sometimes people will take very large data sets and split them up, so you can test them a couple times. And the one I was telling you about, the fight, flight, or freeze, we ran 5 different huge samples. It took forever. So some general rules of thumb. 10 to 15 participants per item. So if you have 30 items, that's 300 plus people. You cannot get it published with less than 100 people. It is not a thing. I know this. We had 98. Okay. So they made us do something else. It was really annoying. But that paper's published and I'm done with it. So 300 is usually kind of like the gold standard. Anything over 100, the closer you get to 300, the better. Okay. I have done this with like one study we had 13 to 15,000 people. Over 300, if it's going to run, it's going to run. If it's not going to run, it's not going to run. So that's why 300 is kind of like the magic spot. Okay. I think the data set we have today only has like 200 some, and it's going to run. So, all right, some separate assumptions than regular data screening. Okay, we've got regular data screening. This is regression on steroids. Okay, it's regression on regression. So all of the normal data screening rules apply. The other big one is the number of variables. If you have a 5-question scale, you can only have 1 factor. So this isn't necessarily the most useful thing for you. Usually you need to start with at least 10. Okay. And this is the only time you'll hear me say this, but the more questions, the better. Or the more items. Because it gives you the opportunity to have more than 1 factor. So you have to have at least 3 items per factor, preferably 4. So if you have a 12-question scale, you can get 3 to 4 factors out of it. If you have a 100-question scale, you can do a lot of factors. If you have 5, you're stuck with 1. For types of variables, they have to be interval or ratio. Sorry, did it lock you out? Sorry, I didn't see you standing there. There was like a weird party going on in the hall. Okay, where am I? Normal data screening, blah, blah, blah. For additivity, we're just making sure they're not perfectly correlated, because then it won't run. Okay, the point is that the questions are correlated, so just no perfect correlations. Okay, so I'm going to go through the steps that you take with EFA, and then we'll try one. So the first question is, does my data set meet the requirements? 2 parts to that. Which one do I have first? Correlation adequacy. So are the correlations large enough to make this work? So if all of your correlations between questions are really small, you have a crappy scale. And that's going to be Bartlett's test. And you want it to be significant. The problem with Bartlett's test, though, is it's a catch-22. Large sample sizes, it'll always be significant. So sometimes people use it, sometimes they don't. But we will test if our correlations are large enough. Do I have enough people? So how many participants do you have? Do you at least have 100? Okay. The other thing you can do is the Kaiser-Meyer-Olkin, or the KMO test. And you want values over 70, but closer to 1 is better. So you can test if your sampling adequacy is what it's called. So do I have enough correlation? Do I have enough people? And that's sort of, it's part of data screening, but it's not. It's like after you have tested for normality and all that jazz, and then you test these things. All right. The real nitty-gritty that we get into is how many components or factors should I have? There's 4 parts to this. So theory is always the best answer. How many factors would you expect? Sometimes you don't have a theory, or if you're me and I'm doing someone else's data, I just don't know sometimes. So people will generally run, if I expect 3, they might try 2, 3, and 4 and see which model is the best. So this is one of the only times that running multiple models doesn't count against you, right? It's not type 1 error. You can also do scree plot. Okay. So scree plots are plot of the eigenvalues. So this is the mathematical representation of variance. This is just the number. And it's kind of like a histogram-ish type thing. The number here is just the largest to the smallest. And we'll get one of these into the output. So you look for sort of where it makes this drop off and levels off. Okay, so this point here is called the point of inflection, where it just is flat. So here I've got one very large one, another very large one, then these two little bad boys, and then this is where it levels off. So I would say there are 1, 2, 3, 4 above where it levels off. You have to look at a couple of these before they start to make sense. But this is like the cut point of the largest drop off. And then I created another one. Where's my other one? So this one's from the data that we have. So they're leveled off here, and then there's 1, 2, 3 above where it levels off. Oop, I'm going the other way. So it's a scree plot. A parallel analysis takes the data that you have and scrambles it. And it takes the eigenvalues of your real data and the eigenvalues of the scrambled data and tests them against each other. So how many eigenvalues are greater than chance given the same data, scrambled data set? So how many of those factors are greater than chance? And the parallel plot is what you'll get here. Okay, this comes from R. This line here is set at 1. It'll always be there. We'll get there in a second, why it's there. But the blue line is your actual data, so FA actual data. The two different red lines are always on top of each other, are the scrambled data. And what it does is it figures out where those two lines cross. So I think on this one it says 5. It's either 5 or 6 of where they cross here. And it will, in the output, it tells you. It says number of factors greater than chance. It tells you. Or number of suggested factors. But a parallel analysis allows you to see how many of them are just sort of better than a scrambled data set. Okay. And we're looking for where the blue and red lines cross, but thankfully it tells you because you can't always read it because sometimes it's tiny on this plot. The last one, which I don't totally recommend using, but we'll still talk about, is the Kaiser criterion. It's an older rule of thumb. Some people still use it, some people don't. Okay. And it's the number of eigenvalues that are greater than 1. It's the old rule. The old new rule is 0.7. I don't know. I don't understand it. So it tends to overestimate the number of factors. So any eigenvalues over 1, that's why this line is here, as it says this is the Kaiser criterion. So there are 3 of them that are over 1, and I think all the rest of these are less than 0.7. So it's still 3. I'll show you how I get that. So what do you do if they don't agree? That is an excellent question. Generally, I tell people to bias towards theory. So if you expect 3, and that's the purpose of what you're trying to do, run 3. If you really are like, I don't know, let's see what happens, try all of them. See which model's best. So if you get like 3, 3, 4, and 6, try 3, 4, and 6. See what happens. It will usually fall out pretty clearly which one works the best. All right. I have never had one where they all said the same number. So we've, in most papers, tried multiple ones and seen what happens. So that's step 2, how many factors? Step 3 is how can I achieve what's called simple structure? Okay. So simple structure is a simplest solution. So the point of these is to make a simple answer. Okay. I have all these correlations. I want to say it's this thing, and then this thing, and that's it. End of story. So 2 parts to that. How do I achieve simple structure? Like, how do I mathematically, this is the math part, make it happen? And the most difficult thing, I think, is this rotation idea. So let me draw it. Let's say in a world of only 2 factors, because I can't draw 3. So this would be the regression equation for factor 1, and that's the regression equation for factor 2. And so you've got data. Okay, so those are your questions. Those are not people. It's not a scatter plot. What happens is we're going to rotate the data. Okay. Factor rotation is just this idea of tweaking the regression equation so that we get the strongest loadings, the b-values, on the questions that matter and the lowest loadings on the questions that don't matter. So you can think of it as cheating. Okay. So rotation allows you to create very strong patterns of data for questions that line up together and weak patterns of data for questions that don't, which is what you want. Okay. For questions like, let's make up this random dude, they wouldn't fit with either one. Okay. So I'm going to start with orthogonal. An orthogonal rotation, Varimax is the most common, makes the factors be totally uncorrelated, meaning they cannot be related to each other. So their regression equations are completely separate pieces of variance, which means it has to rotate at 90 degrees. So let me see if I can do this. Okay, so there's one. But if I rotate at 90 degrees, that means factor 2 has to be here. Okay, so move this way. That works really great for these questions. That's total correct for these questions. Okay. It holds them uncorrelated. Now, the thing about dealing with people is that nothing is uncorrelated. Like, even just random small correlations are normal. So most people do oblique rotation. Ableman is the most common oblique rotation. The names are crazy. I mean, there's Promax, Varimax, Ableman, Promin, there's a bunch of random names. This way we allow them to be correlated. So I'm going to leave factor 1 where it is, but factor 2 can move just maybe this much. I didn't draw this very well, but you get the idea. So now they're not at a 90-degree angle. A much better picture is here. So the orthogonal rotation here forces it to be at 90 degrees. It works okay. Right? The oblique rotation is not at 90 degrees, and it's going to work much better by capturing the question variance. So the short answer is don't ever do an orthogonal rotation. Ever. My statistics professor would be so proud of me. And then this, you should write down somewhere. So why should you never do an orthogonal rotation? If factors are truly uncorrelated, you get the same answer. So if you're running an oblique rotation and they're uncorrelated, it'll give you the same answer as an orthogonal. So why orthogonal rotations still exist is beyond me. But I also work in a field where people are weird and you have to deal with the random correlations. So I would never do one because oblique will give you the same answer if it's truly orthogonal. But really the main point of this whole rotation thing is to get a simpler answer. Okay? And simpler answers have smaller residuals. So this is kind of the Occam's razor of VFA. Smaller residuals always better for you. Okay? So that means smaller error. The other piece to this, so we've got rotation, the other thing is the math. So it's called the fitting estimation. So you'll see the word extracted every once in a while. They're talking about what type of math they're using. So we've got rotation, style, and math together. For EFA, maximum likelihood is the most common, and you'll see it listed as ML. For PCA, it's principal components is the most common. There's also one that's sort of in the middle, half and half. It's principal axis factoring. So that's abbreviated ML, PC, and PAF. We're only going to do maximum likelihood. Okay, so don't say that you ran an EFA with principal components math. People will be confused. So no mixing and matching. Yes, there's our rotation picture. So that's the setup. How do I get to simple structure? I set it up that way. How do I achieve simple structure? Okay, so now that I've run the stupid thing, what am I looking for? We're going to look at loadings. Loadings are slopes. And they're the relationship of that question to the factor. So you can think of them as little mini beaks. And variables are considered to load. That's the word people use. If they're over 0.3. Why 0.3 seems kind of arbitrary. Remember that correlations and medium effect size is 0.3. And that's about 10% of their variance is related to the factor. So we've collectively decided that that is a good number. You can go higher, you can't go lower. So you can cut questions out at 0.5 if you wanted to. Most people use 0.3. Again, this is simple structure, so I want questions to load on one and only one. So we don't usually allow them to do what's called split loading. Or they load on multiple questions. If I want to say this question is this factor and this question is this factor, it can't load on both. So that would be a split variable. Or non-loading ones, those are your bad questions where they don't really match anything. So you just cut them out. So we want variables to load on one and only one and take out the ones that load across more than one or not at all. The other problem you can run into is when you have a factor that only ends up with 2 items, or 1 or 2 items. Then you need to cut out that factor completely. And that's generally called overfactoring. You have too many factors. So let's say you tried to run 6, and on factors 5 and 6 there was only one question. I would cut out those factors and try it again. So what do I do if I have bad items? This is an iterative process. So I'm going to pull up my loading table. I'm going to figure out which ones are bad, take them out, run it again. Figure out which ones are bad, take them out, run it again. So that's why I said type 1 error is not really a thing, because you're supposed to iterate. So think about it as like I'm getting rid of these bad questions as I go. Okay. I have already run the homework as a very simple one. It does not give you too much trouble. If you're having a lot of trouble, you're doing something wrong. So once I get to simple structure, if you can, how do I determine if my model's any good? So how adequate is my model? What we've been doing is looking at p-values. Like the whole semester has been about p 0.05 or less. Whatever. Now we're going to talk about model fit. So we talked about the original correlation matrix and the reproduced matrix, and we subtract them when we get the residuals. We're going to see how much those residuals are larger than what you would expect, because there's always some error. So we're going to use fit indices. Fit indices fall into 2 camps. They're either large or small. So goodness of fit indices are where we want large. By large, I mean like close to 1. Where my reproduced correlation matrix and my original correlation matrix match. So it's a correlation of correlation matrices. Okay. So I want my real matrix and my model to be the same, because that implies that the model I've made is really what's happening in the data. So 2 of the goodness of fit ones, the NNFI and the TLI, or the non-norm fit index and Tucker-Lewis, they're exactly the same. I don't know why it has 2 names. In the output, it's going to be called Tucker-Lewis. So things are excellent over 0.95. They're acceptable, meaning you might get it published over 0.9. Anything less than 0.9 is poor. So think about that criterion for a second. That's really high. is a 0.9 correlation between the two matrices. So kind of a similar rule if you think about 0.05. The residual statistics are just the opposite. So we want small values. It's how big is the residual matrix. These have super fun names. The RIMC is a root mean square error of approximation. Everybody just calls it RIMC. We want less than 0.06. 0.06 to 0.8 sort of acceptable. I don't know what happens from 0.8 to 0.10. I've never understood these rules. Greater than 0.10 is poor. I've always just said 0.6 to 0.10 is in the acceptable range. Mostly because we have a lot of them that are 0.09. I'm not sure what to do with them. RMSR, same rules. Now, these are also applied to structural equation modeling. And this one is the trickiest thing. Sometimes it's called RMSR. Sometimes you'll see it listed as SRMR. They're approximately the same thing. Right? That S is like a dancing S. It just moves around. Where it's standardized root mean residual instead of root mean square residuals. The rules are the same. So we want these to be high and these to be low. Because they're opposites of each other. One of them is interested in how much the two things match. So you want a high match. This one's interested in how much error there is. That's why all of them say residuals or errors in them. The way I keep it straight is if it's got an I at the end, it's a goodness of fit index and it wants something to be high. If it's got a bunch of R's, it's a residual. And that holds true except for one of them that's RFI, because that's annoying. One of the big jokes in structural equation modeling, this is sort of a type of that, is that a new fit indice is born every day. There are so many of them. It's like alphabet soup. These are the most common. All right, so I'm going to look and see if those are any good to tell if my model's any good. Why do I use more than one? Because you can't cherry pick. So what was happening was people would find the one fit statistic that was good and use it. So now most people are required to report several to show that it's consistent across a couple of types of statistics. Without getting into all the math, they do different things to correct for you cheating. So these two have a bias against having more numbers of factors. Like it takes into account the number of things that you've included. The other things that you'll report is reliability, so it's Chromebox alpha. So we'll do 0.7, 0.8 is acceptable. So it's kind of a measure of how consistent the answers are on these questions. And then the hard one is the last one. So in looking at the way they load it, does it make any sense? This was the problem we had with my friend's stuff, was that the questions were loading where they were supposed to. So she was getting questions like, I would aggressively defend myself, and I would run away and hide in the corner. We're on the same factor. That doesn't make a whole lot of sense. They should be different things. So in looking at the questions, can I label them? So do the questions make sense together? Okay. All right, so those are the big sort of 4 questions we have to deal with. Let's try one. Okay, self-determination theory is a really big area. So the scale measures kind of like why are you in college, and it's based on the idea of self-determination. And we're testing if the questions fit a factor structure. So I give you the questions here. I think this is either DC or Ryan. I can't remember. It's 2 big names in that field. And a lot of them are very, have that sort of intrinsic motivation piece with pleasure. I have, a lot of them have sort of like, not extrinsic, but like outside motivators, because I need a job is a lot of the questions, and then they have some negative ones. So I don't know what I'm doing. So we're going to check for accuracy first, min and max values. That's old news. Here's something new. You don't have to do this on the homework one, but I feel like I've gotten this question about 10 times this week alone, so I went ahead and stuck it in here. Reverse scored items. So a lot of times scales have reverse coded items. They're negatively worded so that people can't circle 7 the entire time. Between myself and another faculty member, like, don't get us started on reverse code items because you will see they tend to do their own thing. There's something about negatively worded questions that either the people reading them just like their brain goes, I don't know what it is, but they always act funny, even if they're not meant to. But how do I reverse code them in R? So I marked all the ones in the questionnaire that we should reverse. And we want to switch them so that the scaling is the same. So low scores are still low self-determination, and high scores are still high self-determination. There is a recode function in the car library, I think. But that's not the simplest solution. So the rule for recoding is take the maximum score, so this is a 1 to 7 scale, add 1, subtract the participant score. So if I scored a 7, I would be, and the max is 7, it would be 8 minus 7, I would get a 1. If I scored a 4, I would say 4, so 8 minus 4. And if I scored a 1, I would flip it to be a 7. So it's the max value someone can take minus their score. Don't do it the other way, you'll get negatives. So on our particular scale, we've got 4 that need to be reverse coded. This was just a summary to show you that min and max values were correct. But let's pull up the summary here. Make it bigger. So maybe minus 2 shakes. Where we can see this a little better. So we said that 6 was an example. So here's one way to tell. Or if you don't read this in the back. Here's the means. 5, 6, 5, 6, 6, 2. Okay, so that question clearly isn't doing what we think it's doing, because this is one of the reverse ones. So reverse coded items tend to have very low means when everything else is high, or vice versa. 5, 4.5, that was kind of low, but 2 again. So that's clear to me they need to be reversed. So to recode them, what I did was I just made a table of one of the questions just to see if I did this correctly. So most of the items are towards the bottom, because that's the I don't know why I'm here question. And what I did, okay, so I took the data set of just the questions that need to be reversed, so that's what the numbers are, equals 8 minus, and that same set of questions. Don't accidentally run this line twice or it will subtract 8 again. Okay. So if I do that, and then I look at my table just to show what I did was correct, you'll see that the table should just take all these numbers and flip. So what happens is R does matrix algebra, and through the magic of matrix algebra, it basically takes 8 minus each score individually. So it's taking each person, well, 8 minus each person. And so that's constants. You can subtract constants from matrices. Now, it's so much easier if you have like 30 of them than recoding in car, which is 1 line at a time. So you'd have 1 line for every question. Okay. That's the quicker way. Okay, we get to mice again. Yay! We haven't miced in forever. Y'all are like, whatever. But I do have some NAs because I made some in this data set. Just a couple. Okay, so a couple little NAs. Now I have enough columns to mice. Woo! And generally, let's say you're using a scale and then you want to run an ANOVA on it, and you have every individual question. That's the type of data that you can mice it before you create the total score. So often it's not like in ANOVAs that you can't ever use missing data replacement. It's just that the kind of data that we had this semester, we didn't really do it a whole lot. So for where am I missing? I'm using that same function as before. We're going to do participants first. And so in my made-up data, I have a couple of participants, 8, that are missing 1 item each, here and there. And then I have 1 participant who basically quit. So by first looking at participants, I can get rid of people who got halfway through the survey and got bored and closed it. Because we got to get rid of those people first. That's really common. So I'm going to get rid of those people first. So that just deleted one person. Then I'm going to look by column. Now remember, this is already in percent. And it appears that it's all missing not at random, to go back to something from the very beginning of the semester. So I don't have any columns that are missing more than 5%. I think this is the only one that's got 2 in the same column. Yeah, these two. Yeah. So basically, it just is like once or twice they skipped a question online. So I can replace all of the columns, so I don't have to partition any of those off. Okay. And this is the same mice code that we've been using. Thankfully, it's pretty quick. Create my no miss data set with that complete function. And now I shouldn't have any missing data. So you want to make sure all the missing data is cleared up. You can estimate it as part of the EFA, but it's not as pretty of an estimation that mice gives you. All right. Oop, wrong one. Where are we at? Here. Okay, so we replaced everybody. Outliers is just Mahalanobis. So I know it's regression on regression, but we don't want to do Cooks and leverage because we don't have one regression, we have lots. So just Mahalanobis. Scroll in the right window here. So let's see how many people we got. So we have 32 degrees of freedom because we have 32 questions. So that gives us a big cutoff score, 62. And I have 11 outliers. You might get a slightly different number because remember we're all micing slightly differently. Here's the deal. They don't tend to make a difference. We're going to exclude them, but honestly, meh. 11 people in this type of analysis doesn't tend to change the answer much. But I'm going to dump them. Let's get rid of them. Yeah.
So if you were doing this for real with your own data set, would you want to like run it?
With and without.
Yeah.
Usually that's what I do is with and without, and it doesn't make a difference, so I just leave them in to have more people. Because there's so many, because there's usually so many people and so many questions that those couple of patterns don't tend to mess too much up. All right, so we got rid of those people. Oh, I actually had 12 when I ran this the other day, so slightly different answers. That's because of mice differently. In general, we want correlations. EFA, the whole point is correlations. So we're just going to make sure that we don't have anything that's too correlated, so when this runs, you know why it doesn't run. This is going to be a big table. So mainly I'm looking for anything that is a 1 that's not this diagonal. So a perfect example of this happened this year. I do have a plus, that's okay. Is a 1. We're working on one right now that has 104 questions, which is kind of like the largest correlation table you've ever seen. And the person running the analysis was reverse coding items and accidentally saved it as a different name instead of overwriting the original name of the question. So we had 2 columns in there. One of them was regular coded, one of them was reversed. And so it wouldn't run because the columns were perfectly correlated because they were just reverse coded. That took us forever to figure out because the questions were right next to each other. So it was like 2 little ones like right here in the middle. I had to dump it into Excel and tell it to highlight the ones before I finally saw it. It was like 1 letter that was wrong. That was screwing up our whole analysis. She was like, oh my gosh. I was like, I totally would have done that. So I can't spell, so we're cool. But I think I like a week. Poor Rachel. Trying to figure that out. If you want to look at the real correlations, you can, but it's just like impossible to read, so meh. Okay, we have been running real regressions and doing the data screening on real regressions, but we have to go back to something fake because this isn't a real regression. So we're kind of going a little bit backwards. But all this code is the same that we've done before. So let's look at the residuals. meh. It's okay. It always gets us one person out here. Okay. And this is real data, so it might be kind of messy. That's all right. And then this, homogeneity-wise, is like kind of iffy. Homoscedasticity-wise, the problem is it's being missed. So it may be a little heteroscedastic. But the thing about that is that it might be there are several bad questions. And sometimes with bad questions, they're going to have high residuals because the questions just don't correlate well with anything else. So I tend to have really, like I've had pictures that are especially bad, I'll run it after I eliminate questions just to see if that made it better. Okay. This isn't too crazy, but it is a little triangle-y. Okay. So all that's what we've been doing all year, so let's get down to the good stuff, which is the new stuff. So do we have a good data set for EFA? Well, I hope so, since that's the point. How many variables do I have? Well, I have 32, so I have enough for multiple factors. I could probably get about 10 factors out of this if I put 3 on each one. You don't want to have that many, though. My scales are at least interval, which is good. At this point, I think I have 194 in the one we're running right now, but I had at least 193, which is over 100. It's not quite 320, but it should be okay. You should have psych on your computer, but you may not have GPA rotation. So you might have to install that one kind of quick. It helps the rotating part work better. Make this a little bigger. All right. So if you've done your data screening, you have this coral data set, which is the correlation table, making sure it didn't have any ones in it. So the function is cortest.bartlett. Okay. It's the correlation table, comma, the number of observations. So that's why the in-row thing. So what that gives you is chi-square. Are my correlations larger than 0 is effectively the question. And yeah, by a lot. But I've got 496 degrees of freedom, so, you know, take it with a grain of salt. So you would write that up with chi-square. It's 4,000, p is less than 0.01. Yes, I have large enough correlations for EFA. Now, sampling-wise, do I have a good sample for this? And that is just KMO. These are thankfully easy. Of our correlation table. And what it does for each question tells you the sampling adequacy for each question, which is looking at the spread and the range of the data, that sort of thing. But generally, people report the overall MSA, mean sampling adequacy, as 0.92. Remember, we want values over 0.7, 0.8, 0.9 is really good, so we're doing good. There's only a couple that are kind of low. So question 28 might be kind of bad. If your MSA is really low, you might be able to figure out if it's a couple of the questions that are bad, and just go ahead and toss them, or even get started. So I have a big enough sample and a good enough correlation. You can prop that all the way open if you want, so it doesn't lock you out, since the live people left. That answers the first question. Second question, how many factors? So my number of factors here, I just called it no factors. To run a parallel analysis, it's fa.parallel. So my favorite part about base R is sometimes they don't think about things when they name them. There is a factor analysis in base R without loading psych. The abbreviation is factanal. I was like, I can't. It does not run as well as psych does, though. So we're going to use FA instead. The psych people do think about how they name things, which is why it's FA. It also doesn't do parallel analysis, which we need anyway. So FA parallel does the parallel analysis part. no out is our data set. FM, factor math, is maximum likelihood. FA, factor analysis, is factor analysis. You can do FA and do both, and you'll get PCA and EFA at the same time, but we're specifically doing EFA, so just FA. When you run that, you'll get two things. The scree plot. It's grumpy with me. Hold that thought. I may have to make it bigger. There it is. The scree plot. And down here it says parallel analysis suggests the number of factors is 5. So the number of components is NA because we didn't ask for it. All right, so I'm looking at my scree plot. Let me write this down. So theory suggests 3. There's 3 parts to self-determination theory. Their parallel analysis suggested 5. Okay, so far not good. What does the scree plot suggest? I would say 3. Because all of these are pretty, I mean, they're still dropping, but not that much. So it's pretty flat. There are 3 above that. Scree plot suggests 3. What about Kaiser? Now, the thing that we saved has fa.values. Those are the actual eigenvalues, but I'm a big fan of not looking at numbers if I don't have to. So this sums up the number of ones that are over 1. There are 3. If I look at the new criterion, so over 0.7, there's still 3. So we're going to run 3 factors, because 3 is a really common theme. And I'm biasing it towards theory, so I have 3 of them. We're going to try 3. I could try 5 if I wanted, but we're going to stick with 3. So there's a lot of talk about like all these different rules, and it's only like 3 lines of code, which is normally reversed, right? Normally it's like, here's the rule, here's 8 lines to get it. But parallel analysis is pretty cool. Can we get to simple structure? Okay, so I've got round 1. So the code is just FA instead of no parallel. Now we're just running the factor analysis. Dataset name, number of factors equals how many from the previous step. Rotate is Abelman, because we're going to stick with no oblique rotation. Math is ML. So this is the setup part of it. And we're saving it so we can use it here in a little bit. So we're going to run that and then look at all the output here. So make sure I haven't skipped anything. Talked about all of this. 3, 3, 3. Yep. Okay. So looking at all of the output, this is unfortunate amount of output, but where we're going to start is the top. So you want to look at this thing. So what's going on? It gives you your factors. ML for maximum likelihood. And then it says 1, 3, 2, which is a little weird. Yours might say 1, 2, 3. What's happening is it gives them a label based on the eigenvalue number. And sometimes they'll switch around, and that's okay. So it doesn't matter what order these columns are in. But I have 3 factors. H2 is commonality. So how much of that question is accounted for by these different loadings? So higher commonalities indicate that it loaded well in at least one of them. U2 is the reverse, it's error. So these 2 add up to 1. It's basically the split of the variance. This is how much variance is accounted for, this is how much variance isn't. And then complexity, which not a lot of people use. But how do I interpret this? Well, I'm going to teach you an Excel trick. So I always highlight everything, copy it, just the table. Some Excel magic for today. If Excel will open, there we go. Okay. And I'm going to paste it all. If your Excel is like mine, it pastes everything in the first column. This is annoying. Okay. So when you have it pasted, it's all highlighted. Okay. click on Data, Text to Columns. If you haven't ever met text to columns, it's like your best friend when it comes to formatting tables in Excel. Just hit Finish. It'll figure it out. Sticks them all in different columns. Oh, it gets better. Just wait. Highlight the 3 factor columns. And this is under Home in Excel. There's this conditional formatting box. This is really great when you have 104 questions, by the way. Okay, so under conditional formatting, highlight cell rules greater than 0.299.
Yeah.
I swear I taught this. I swear I taught this last time. Anyway, here it is now. Glorious.
That's amazing.
Sometimes you'll get negatives, so what you can do is highlight less than negative 0.299. Negatives do happen. This data set doesn't, but they do. If you want to get even fancier, hit Data and then Filter. You can do the little drop down here, and you can filter by color. So I can look at all the items that loaded on factor 1. Look, we got 2 bad items. This is born out of necessity. Anyways, the filtering is just an extra piece. But basically what I'm doing, and I put this in, I didn't put that Excel how-to. If you don't remember later, I can show you. I put this table in here just so you can see. Okay. Now, this is the solution we have right now. We rotated it, and we've maximum likelihoodded it. And here's the B value for each factor, for each question. And I don't want them to load across 2 or not at all. So each row should have 1 pink cell, and that's it. So the first one's fine, second one's fine. This question 4 is bad. It double loads or split loads. Okay. 5, 6, yeah, most of them are pretty good because this is an example. 15 is also bad. Oh, looks good, looks good. All right, so we didn't have any questions that didn't load. So the line is completely empty, as in they don't have anything above 0.3. That's also bad. That Excel thing is like, well, that's too much for me. I don't want to do that. You can look at one line at a time. The tricky part is don't look at H2 or U2. Right? We're just looking at the first 3 here. So question 4 is bad because it's got 2 3s, and 15 is bad because it's got 3 and a 4. So before I even look at any of the stuff on the bottom, so none of this crap down here, I'm going to rerun that again. I've called it round 2. And I've dropped column, so minus column 14 and 15. Just got rid of them. And so I would do that exact same thing again. Take all this stuff, dump it into Excel. God, be bigger. Always do 2.299 because 0.3 happens every once in a while. So now I can see that the questions look like they're not double loading. Plus, I've already done this once. So they're all loaded on 1 and only 1. That's the simple solution part. So 1 factor only and not double or none. All right. So we're going to pause there. Let me finish this. All right. So we finished with simple structure. It's a little bigger. And getting every question to load on 1 and only 1 item. And so the last piece past simple structure is this model adequate? So is the model any good? And for that, we're going to use the final output and only the final round. So you can look at the model statistics for each round. They should get better when you remove bad questions, but generally people just talk about the final one. And remember, this is the alphabet soup of things. So one of the first things, and this is at the top of the final round of output. I'm sorry, it's not at the top. It's right underneath the loadings. It's at the top of the bottom, so to speak. It tells you how much variance each factor accounts for. So ignore sum of squares. Okay, those are the eigenvalues. Here is what I'm interested in. So that first factor is 31% of the variance by itself. So it's a huge factor. And then we've got two also large factors. You think about this being r squared. So we're accounting for total 60% of the variance. So that's one of the big differences between EFA and PCA. Remember, PCA accounts for all the variance. EFA only accounts for overlapping variance. It also shows you the correlations between factors, okay, between the factor averages or totals. So the first one and the second one, which is 3, I guess, are moderately correlated, but 2 and 3 are really correlated. You don't want those to get up into 0.7 and 0.8, because then that implies that there really should be one factor instead of multiple ones. They are correlated. You probably would expect them to be correlated, but that's really good evidence on why oblique rotations are so important, because otherwise you would have forced that correlation to go away. And that's a good quarter of the variance that is between the two. So we want to leave it as oblique. And we don't want them to be super correlated, or that implies we should collapse factors. Okay. So is my solution adequate? Well, we look through this output for the fit indices. It's not the easiest thing to read, but here's RMSR. So the root mean square of the residuals is 0.05. That's in the good range, the excellent range. Scroll down some more, we get the RMC, and that's in the okay range. So 0.10 and the 90% confidence interval. It's not 95, it's 90. It's a little weird. That's normal. So 0.08 to 0.9. You want that range to be kind of small. And then here's the Tucker-Lewis, or the TLI, and that's not in a good spot, right? So we want that to be 0.9. 0.95 would be better. So 0.82 is kind of crappy. So 2 of our fit indices say it's okay. One of them says like, oh God, no, it's bad. What you don't get in the output is CFI. So I've written the code to calculate CFI, so don't edit it, because then you'll get CFIs over 1. So if you get a CFI over 1, you've done something wrong. It should be slightly larger than TLI. Okay, so at 0.82, it should be just a little bit bigger than that. So what it's doing is it takes 1 minus your model, the final model, chi-square, minus degrees of freedom, divided by the null model, minus degrees of freedom. So what that does is it accounts for the number of factors. This is the degrees of freedom part, or degrees of freedom in this model, sorry, the number of participants. And the chi-square kind of accounts for how close the two models are to the original correlation matrix. So it's 1 minus a ratio of your model to the residual model. Sorry, the null model. You want that number to be big, because you want your model and the null model to have a very to have a log odds essentially towards your model. So DOF is degrees of freedom, statistic is chi-square for your model, so I just called it final model. Statistic minus degrees of freedom, null chi-square minus null degrees of freedom. I don't know why they're not like your chi-square, your degrees of freedom, but this code should run. As long as you save the last one as final model. So what I did was I took round 2 here and just copied it next to final model. So I could run, maybe my CFI, these 2 lines to get CFI. So it's 0.86. Okay, why go through all the trouble? CFIs are probably the second most popular one to report after RMC. Usually people have both. And if you tell somebody, well, I don't have it because I don't know how to calculate it, definitely going to look like an idiot. So this is just an easy way to calculate it. So 0.86, still bad. So I have 2 that are good and 2 that are bad. So it would be a tough sell, I think, to a reviewer. But hopefully they're at least reliable. So we're going to use alpha. The psych package has the alpha function. And what we're going to do first, and this actually would work for lots of different things. It's kind of a cheat that I probably should have taught you earlier, but whatever. So we're going to save each of the columns that the factors are in as a separate little vector. So where did I get these numbers from? Well, that final table here, everything that's highlighted goes into factor 1. So I've got question 1, question 3, 7, 8, 10 through 12. So where it loads is what factor it counts for. So I typed all that up, sorry, too fast, here. So factor 1 has the most questions, factor 2 has less, and what you'll see is that factor 3 is all of our negatively worded questions. That's why I said they're dumb sometimes, because they act funny. They loaded on their own factor. That's usually a sign that you should get rid of them. They're not doing what you want them to do. So these numbers came from that table of the final loadings. They should not overlap. As in, factor 1 should not have 3, and factor 2 have 3 at the same time. So then what we'll do is do alpha with no out. And normally you put all that C stuff right there, but it helps if you make it separate for reasons I'll get to in just a second. So I'm on line 95. So all these 3 things do is just tell me what columns to use. Now I'm going to calculate the reliability for factor 1. Okay. It gives you so much output. I don't understand this. So much output. Just give me a number, right? Instead it gives you a ton of numbers. What you're looking for here is this, or basically raw alpha. So the reliability for the first one's 0.95. Anything over 0.7, 0.8 is good. 0.95 is really good. So that first question is pretty reliable. About the second one. Oh my god, all the output. 0.86, it's pretty good. Okay. The more questions you have, the more reliable a factor will be, no matter what. And then, oops, I ran the wrong thing. Factor 3 is 0.9. Okay, so it's not like factors with small numbers of questions are necessarily going to be bad, but if you had a factor that had 3 questions and you added 1 more, it would automatically kind of bump up. Because the more questions you have, the easier they are to hang together. But the last one only has 4, and it's really reliable. I'd argue it's not a very good factor, and you'll see why, hopefully. But it is reliable. So the model has mixed reviews, so to speak. The factors are all reliable. And then we're in with theory. Well, theory and creating scores. So can I describe what all this means? Because you can have a perfectly adequate model, like a good model that is very reliable, but the questions don't make any sense. So you still got to be able to sell people what do these mean. So I'm looking at my loadings. I got 1, 3, 7, 8. Okay. Let's look at those questions. Okay. So 1, pleasure and satisfaction learning new things. 3, succeeding. 7, pleasure surprising in my study. 8, intense feeling I experience. It's very sort of hippie. 8. Of course, I always think the self-determination stuff is a little hippie. So 10 through 12. Oops, sorry, wrong window. Okay. College makes me feel important, allows me to learn subjects that are important, allows me to learn things that are interesting. So the theme here, down, is like the sort of intrinsic motivation, like love of learning. That's what I would call that. So I made this up. I looked at what all the questions were, and made up a title for it. So that's what you're doing in this part. If I look at factor 2, it's all the career questions. So things like, because I need a degree to get a good job. I need these skills to get a job. So they were all job-related questions, which is really a sort of extrinsic motivation. So career goals is what I called it. And then factor 3 is the messy one, because it's all of our reverse-coded items. And there are things like, I don't know what I'm doing, life is hard, I don't understand. Okay. So I called it doubts about college because I didn't have a really good answer. But anytime that happens where all of the reverse-coded items load on one, that's usually a bad sign. Because it implies that people are not interpreting those as simply kind of the opposite of your other questions. They're seeing them as something totally different. If you're okay with that, that's fine. But generally, most of us are like, oh, reverse-coded items. Ugh. The best person to ask about them is Dr. Vizio. And give yourself at least a good hour for that rant. I listened to it one time, and I was just like, ditto. Because they act funny. They always do weird things. If they stay, oftentimes they'll get eliminated because they don't load on any factor. Okay, so what do I do with these factors? Now I have them. The model seems to be okay. I can label them. The only real problem is that TLI and CFI stuff. Generally what people do last is either use those factors to predict something as a convergent and discriminant validity test. We're not really going to get into that, but instead, at least we're going to calculate average scores. I see. So if I wanted to use these to then predict something else, or if I wanted to just calculate some more statistics on them, I need an actual score for the person. Because right now I have, here's this factor thing, here's all the questions I think are important. Moving on. Okay. So this apply code, we've used apply before. Remember apply we used for percent missing. Will allow me to calculate the average score for each person or a total score for each person. Sometimes you want to do weighted scores. It's a little more complicated, so we're going to do the easy ones. Okay. So the reason I saved them up here as one over here is because I used it again down here. Okay. So I have no out factor 1. Okay, don't call it actual factor 1. That's you'll overwrite your other code here. So apply on these columns by row and create an average score for each person. So what that's doing is taking all of those columns and then averaging across and giving the person one average score for factor 1. I repeated the same thing for 2 and 3. If you wanted total scores, you would do sum here instead of mean. So when I run that, now at the very end, I have their average scores. So for each person, I have what they scored on each factor, which I could then, use in repeated measures regression. I could do an ANOVA to see if people are different on these factor scores based on gender or some other variables. I could use them to predict other things that I think are interesting. So being able to calculate these is like an important thing to know how to do. And then I just calculated the averages for them. So for factor 1, the average is about 5 points. Factor 2, 6 points. Factor 3, 6 points. So what does that imply? Well, factor 2 was job related. So people are really saying, I'm going to college because job, money, eating. Right? But they're also pretty on the reverse of a negative 1. Because remember we reverse scored this. So they're not really doubting themselves, which is good. And the lowest one is this sort of love of learning, which as like a professor, I'm like, okay, I get it, but oh, that sucks. Right? And then I calculated the standard deviations for each one. Okay. And they're pretty small. So this is very top-heavy scale. Right? This would be very skewed towards the top. So people love school and everything's wonderful. Until the last day of class, right, and you're like, oh, now I need a job. All right. So that is the end of EFA, and then I have an example write-up. But the hardest thing, I think, is this table. Okay. What I did to make this table, since we've been kind of talking about Excel, let me copy this. So I took my final loading chart. Scroll. And then Excel opened, and everything was glorious. There it goes. Good gracious, Excel. All right. So I have my final loading chart. And what you can do to sort it, because people always sort them so that they look pretty, don't just copy my table and cut and paste it and say that you sorted them. That gets on my nerves. Okay. Actually sort them. So what you can do is highlight all the questions. Tell it to sort. So data. I picked AZ sort. Sort by column 2. Go away. Okay. And then largest to smallest. Okay. So that put all of those questions together. Okay. And then if I wanted to be really fancy, I'd actually sort by the question. Shrink. Okay. Then highlight just this one. Okay. AZ sort, column B, no, C. A, B, C. Yeah, C. I did that backwards, but largest to smallest. Either way is fine, so that they kind of stack up together. Because then, instead of having the question numbers, what somebody might publish is the actual words, like the questions, so you can see the factors a little easier. So you're not like, okay, 1 is here and 1 is here, 3, 4. Instead, it's like, look, all of these go together. All of these go together. Look at these. They all go together. What you don't want to do, because it's really tempting to do, is click Sort, tell it to sort by column B. Okay. And then, okay, I'm going to sort. Okay, now I'm going to sort by column C and expect it to stay. Okay. It doesn't do that. Okay, so highlight all of them, sort, highlight just the next set that you want to sort, and then highlight the last set to sort. So you can't tell it to sort by this, then this, then this. It doesn't quite work that way. All right. So that should be good.